And we'll start off by going around the room as is customary for everybody to say who they are. Take it away, Dale.
Dale Tavey, editor.
Dale Parton, new treasurer. Say your name. Kenbert. Bob Tremblay.
Jeff McLeod Outreach.
Tom Servanac.
Tina Long.
Ken Ward. Mike Bowles. Peter Ricketts. Christopher Esbrook, member. Jerry Ravello, member. Michael West.
Jamie Clark.
Patrick White, member. Jonathan King.
All right. Do we have any new faces tonight? Excellent. How do you find out about us?
I'm their son.
Okay.
So we brought him along visiting from Seattle.
Very cool.
Want to be our treasurer now?
First secretary.
We are pleased to let you know that Metro Detroit actually has cloudier weather than Seattle, statistically speaking.
Yeah.
That's why we have so many astronomy clubs. Okay, so presidential order of business. Big news is we do have a treasurer. Dr. Dale Parton stepped forward to fill out the remainder of the year. We went to the bank today and got him fully on board. So he's got the checkbook, he's got the bag, he's got the cash box. Full details of the WASP treasury situation are in the WASP. So we are good until election time. Just saying.
What do you say?
Which is not that far off. We also still don't have a secretary. We've been relying on a bot and Dale Themey. The bot does an okay job, but we would love to have a human being in the role. If interested, see me at the break, mail me, text me. I don't care. I would love to have a treasurer. Because the most important vote of the year is coming up, and that's voting on our insurance policy for Stargate. And that could get contentious sometimes, so we don't want to tie. We'd love to have a seventh member. Okay. Big news. Normally Jeff would cover this in outreach, but since I just got the lowdown from Cranbrook personally, I'll fill you in on the plans for this month's outreach. So, Solar Discovery Days, right here in Cranbrook Institute of Science, at the beautiful little herb garden by the main entrance. We want solar telescopes there from 11 to 3 p.m. Cranbrook will be providing snacks and drinks. Then they want us back that same day because it is the peak of the Perseid meteor shower. So next Wednesday, the 12th. The official start time of that event is 8 p.m., but they say don't rush. It doesn't get dark until 9:30. So if people are in place in the west entrance with their telescopes, lawn chairs, blankets, whatever, we'll be in good shape, 9:30 or so to entertain the public, which believes that meteors can be observed through telescopes. Yes, Jonathan.
If you do have a way to safely show people the sun,
We understand some of you have plans to be elsewhere for the solar eclipse, but for those of you who are staying here in Metro Detroit, we need you. Then after the Macomb meeting, we will be returning to Cranbrook on the 27th, again for a nighttime event for the lunar eclipse that follows the solar eclipse. Should be a lot of fun. We've had multiple lunar eclipse events here at Cranbrook that were great, except it was dead of winter and we were miserable. This time it's going to be the dog days of summer, so we should be fine. So again, Cranbrook will provide snacks, drinks, coffee, what have you. And that party will be rolling until the wee hours of the morning. So please mark your calendars, send us an email, outreach@warrenastor.org to let us know that you're coming and what you're bringing. And we will have a really good time here at Cranbrook on the 12th and then on the 27th. And I'll leave the rest of the outreach stuff to Jeff because there's plenty. Other presidential business. The banquet is only a few months away. We love to give service awards to acknowledge our distinguished members. If you have a nomination for somebody for one of our service awards, please email the board and we will take that into consideration. And finally, the next Cranbrook meeting is going to be on the 21st of the month in September. So we will have the next Cranbrook meeting after the September Macomb meeting. Mark your calendars. Cranbrook shut down during the second week of the month. It's going to be weird, but we're rolling with it.
It's also after Astronomy Beach.
It is after Astronomy at the Beach, so Jeff will be talking about Astronomy at the Beach, but it'll be after Astronomy at the Beach. So yes,
Yeah.
18th and 19th.
Oh. This is.
This is the last Cranbrook meeting until after Astronomy at the Beach. We have 2 Macomb meetings, mind you, in the next month. So anyway, it's going to be weird, but we'll roll with it. And with that, I'd like to turn things over to First Vice President Jonathan Cade for his report.
Hello. I have good news for you, unless you were hoping that there would be an opening in the presentation schedule before the end of the year. I think we have all of the presentation spots filled with one slight asterisk for our October Macomb meeting. I'm really hoping that David Levy is going to be able to join us because I believe we are going to have our first ever astronomical poetry festival. So as our long-term astronomical poet, David would be the best person to be there. I'm still waiting to hear from him on if he can be, but I have some friends in the poetry community in Metro Detroit, so they're looking for people to come down and talk to us as well. So I also had a really exciting talk for the Macomb meeting that is coming before the Cranbrook meeting in September. We are going to hear about one of the strangest astronomical observatories I've ever seen that I had never heard of before. And we're going to hear about it from somebody who was there for several years and had the run of the place. So he's going to talk about the history of it and why it looks like it was a rocket launch compound instead of a astronomical observatory and why it is sadly no longer on the shores of Lake Michigan. So that's a little preview of the rest of the year. And also, if you have a presentation for next year, I'm taking reservations.
All right. Thank you, Jonathan. Treasurer Dale Parker.
Until you get.
Dale says we have money. We do. Read the WASP. We've got a lot of money.
Short and sweet.
Yeah.
Buddy.
Secretary, AI bot, pass. Read the minutes in the WASP. Again, Dale Teamy has been doing work behind the scenes to pretty those up to make them presentable. Outreach, Jeff McLeod.
Sure.
It's because she's not in front of me. Yeah, I'm so sorry. I can't see the screen.
That's all right. Did you want me to go on now or Jeff first?
Go ahead. Jeff
Oh.
and me.
Okay,
You outrank him.
all right. All right, well, thank you. And hello, everyone. Last open house we had was, of course, right after the picnic, same day. We started out with kind of cloudy sky and hazy, and later on it kind of stayed hazy, even though it cleared up. Pretty much the whole sky cleared up, but yeah, it remained, I think, probably from the smoke. We had the haze. We had a lot of people attending, roughly about, I would say somewhere around 60 people, maybe more, between visitors and members. We used the 8-inch refractor to observe Venus, the moon, and a few double stars. And Jonathan Cade had the 22-inch outside the shed. So he observed the moon and some deep sky objects. And we have a bunch of scopes set up on the north side of the observatory as well. While we were there, of course, we also had a a donation, I should say, of a telescope from Brian Wazinski and his friend. It's a 160 millimeter Newtonian reflector with equatorial mount, tripod, and a number of eyepieces. So thanks to him for that and to his friend. The picnic, I think we'll be talking about it later on, but it was excellent. It was fantastic. Anybody who showed up, I think, enjoyed it tremendously. I know I did with my family. The next open house, we're going to have two of them actually in August. So the Perseid meteor shower is this coming Saturday, August 8th. We're starting Saturday only because we're having it on Saturday because it's in the middle of the week. So if you're available, not doing anything, come on out and bring a lawn chair or a blanket, whatever you want. And hopefully we'll have some clear skies to see some meteors. The next regularly scheduled open house is August 22nd, starting at 7:30. So hopefully we'll see everybody out there. The open house for the meteor shower should start about 8:30. So come on out while the sun is just setting, so you can set up, find a place to sit. Other than that, we're all set. Everything is good at the observatory, equipment and so on. And we have a couple of scopes available for checkout if anybody's interested. The rest of them are out already. They've been out for a little while. And that's all I have. Thank you, Dan.
Yes, we do have a piece of lost property at the observatory. We have Mark Kenzier's cup.
I got it.
He's got it. Okay. We also had a pair of sunglasses reported lost.
That's what we're looking for.
And so if anybody acquired a pair of sunglasses that are not yours, please see Ken Burton in the front row because he would like to have them back. Okay, as Ria had said, the picnic was exceptional. We had great weather in spite of the haze, great company, great food. Everything was wonderful. And a round of applause for Mark Kenzier, who's arrived because he handled our grill. And with that, over to Jeff McLeod.
All right, so Diane covered all of the Cranbrook stuff that's happening just this month, and it's a lot. But if you're interested in any of that, feel free to talk to me or her. We can let you know how to help. You guys are going to Tecumseh in September.
Yes.
And then there's a Belleville event. It's not till October, so we got time, but it's a new thing with a couple of different clubs. It'll be interesting. So more to come on that. And then I don't believe I heard that Jennifer Dye found anyone for the October. She's looking for a digital presentation for the Detroit Public Library branch towards I think it's the 27th is what they want, but she's flexible. So if that sounds like something you're into, let me know. Astronomy at the beach, I'm hoping to send out our like WAS in-house volunteer email like tomorrow, where I kind of hit all my regular people, see who's doing what, ask them to forward that to anyone they think is interested. So if you want to be on that list, let me know tonight. Some of you are going to be on it whether you want to or not. And we'll start trying to figure out how we're going to cover everything. Hopefully most everyone that was helping last year is helping this year because we did pretty well last year. Let's see. Let's do this now. I have the last Night Sky Network Outreach Award pin for 2025. Yes. Ben Lord. I've been waiting for you to show up.
Congratulations, sir. Thank you.
Ken did a lot of help with the big job last year at Astronomy at the Beach and other events. So I'm glad that I can finally throw this away. It's been sitting in my car for months. Lastly, I'm turned out on outreach at the end of this year. I've got like 6 people that want to do the job. It's super competitive. So if you want to get in the mix, because this is a job that people fight for, okay? You don't just fall into the outreach position, okay? It's not like some of the other positions. Really,
Fix you up and fix you up.
uh, please save the cloth. What, outreach?
Yeah, there's an outreach event at Milford, at the YMCA.
Ilford?
Yep. it's supposed to be-
Nobody tells me.
Well, I pulled this email and I can for you.
October 23rd or August 22nd.
Thank you.
Dave, we're gonna talk about your involvement in the club, pretty soon here. I want you to be the next outreach coordinator. All right, send me an email because I don't think I have anything on a Milford event. When is it?
It's October 20, I keep saying October, August 22nd at the YMCA in Milford. GM and Ford were out there, whatever the last one was. I want to say, I think it was in March, but it was cold. So it might have been March.
Okay. Is it a public event or
Yeah,
are they
yeah.
just?
It's
Okay.
open to the public, yeah.
Okay, I'll get the details. I'll get them out to the rest of the members. Might be a fun event to go to, and if you'd like to help out, that would also be great.
Well,
All right.
I plan on being there anyway, so.
Cool.
He made a turkey. See, star, are you there? But
All right, we also have the, for any of you who goes up north, we've got the first ever Dark Skies Alcona Friends of Negwagon Dark Sky event at Negwagon State Park. Jonathan and I will be there on the 15th of this month. Adrian Bradley might make an appearance, so is he coming for sure? Excellent. And if you want to venture up to Negwagon State Park, we have a field that can be used for camping, RVs, what have you. We have a couch. We have 2 couches. So please come.
What's
We
the
would love to
date?
see you. August 15th.
Oh,
Most undeveloped state park in the state of Michigan.
and where is it again? I'm sorry.
Black River, Michigan. How do I do a map on this? Here. South of Alpena. Okay, with that, over to publications.
You have a question? What's the name of that park again?
Negwagon.
Okay, thank you. Was the one that asked the
Negwegon.
question.
Yeah, Negwegon.
And it's in the Wasp.
It's in the WASP. Okay, publications all good?
Yeah, all good. WASP is online, and make sure you follow the events calendar and show up to the events we're doing.
Yeah, we have a lot of events.
Are the calendar, I don't remember seeing any events on the calendar though. Are they there? I don't,
They
Which
should be-
calendar?
on our website. I think the only thing there is meetings. That's last time I looked.
Yeah, I think the website calendar, I would look at the Wasp and the meetup.
Yeah,
Okay.
okie dokie. That concludes officers' reports. We've got a solar report from Bob Tremblay.
Dale, can you read that?
Here.
You can, it's open if you pull it over.
Oh, okay.
Read it over. Don't forget to share it on.
Yeah. Zoom back over here. Oh, man. Oh, for crying out loud. Doing this 2 screen is crazy. That's it. There you go. Should know which one do I share?
Down at the,
There.
got it.
Not that one?
It's in blue. Yeah, click share.
All right.
There you go.
All right, so how do you scroll this down? Gosh darn it.
Just hit the single line and then mouse over that. Sorry, you have to kind of do it backwards, but hit the single line at the top of the video with it.
I am not understanding what you mean.
Just go ahead with the solar.
All right, well then, okay. A coronal mass ejection left the sun on August, it hit the Earth on August 2nd, sparking a G2 class geomagnetic storm. The storm is over now, but there's a chance it could flare up again today. And as it moves through the CME's magnetized wake, I've got a video here, which I'm not going to play, of this thing down here of the CME hitting the Earth. There are, how do you scroll down? That's what I got. Or search these solar. This sort of so lights down. Oh no. I'm gonna have to have Dale share this next time. This is crazy. I can't do both of these. Anyway, there is a thin elbow-shaped coronal hole in this on the sun, and it's rotating in to face the Earth. Yeah, right there. Yeah. Right in the middle. You can't miss another. And so there we go. So yeah, there's an L-shaped coronal hole that's rotating toward the center of the sun. Solar wind was quiet this morning, but over the last 24 hours, it was pretty darn high. Sunspots, yeah, keep going down. We've got 6 numbered sunspots on the sun's face, and one of them is pretty darn big. Yep. That's 4498. 4498 has a beta delta magnetic field that harbors energy for M-class flares. Keep going down. And there is a picture of it from somebody's solar telescope from Facebook's solar activity group.
The legendary Thierry Legault.
Oh my.
Is he legendary?
Yes.
That's
Really?
He's the guy who
That's cool.
photographs the ISS in front of the sun and moon all the time.
Yeah, so these things. I keep saying that solar astronomers in the 1800s would cry if they saw the pictures we had today. This is a graph from NOAA. This shows solar flares over the last 24 hours, and we've got a couple C-class flares, not very much. Coronal loops keep going down. We've got some pretty darn big coronal loops. They're just beautiful. Look at that. That's crazy. I love it. Coronal loops galore. All right. Now, I'm getting off topic here, but this was my Windows. Yeah, just leave it right there. This was from the Microsoft Windows Weather app, and I'm not really sure what that's trying to tell me.
I mean, it looks like the cloud is in front of the moon.
That's not the moon, it's the sun.
Oh.
So, and it's got it's an eclipse. So astronomers are going to be confused by the Microsoft Weather app. Well, I was thinking, like, if you're going to be showing a night sky, why not do something like the Big Dipper or the Milky Way? The best clear skies have stars. So anyway, I just thought that was pretty darn funny. All right, scrolling down here, this is pretty interesting. I get news alerts when Vatican Observatory adjunct scholars post new research papers, and this one came up. Before today, astronomers confirmed roughly 3,000 to 3,700 ultra-cool dwarfs and brown dwarfs. A new research paper co-authored by Dante Minetti, an adjunct scholar at the Vatican Observatory, and a student from the 2018 Vatican Observatory Summer School, the 2 different ones, says that a catalog of about 11,800 ultra-cool brown dwarf candidates has been produced using Catwise, 2MASS, and the Gaia DR3, all major astronomical surveys. I've never heard the phrase ultra-cool dwarf, so I had to look it up, and that's a stellar or substellar object with an effective temperature lower than 4,400 degrees Fahrenheit.
So pretty interesting. So down here, I also get new asteroid name discovery, and I have found a couple of people that are solar researchers. So this guy, Gary Zank, is an American space physicist who developed first modern models describing large-scale heliospheric interactions in the local interstellar medium. His first two papers predicted the existence of the hydrogen wall, never heard of that, adjacent to and beyond the heliopause, which, when confirmed, was regarded as one of the as the major science physics discoveries of the 1990s. So there's a paper for someone. I never heard of that.
I've covered that in the
Yeah.
interstellar object talk.
And David Gary Sibek, an American space physicist who revolutionized our understanding of how the solar wind interacts with the Earth's magnetosphere and ionosphere. He established how variable solar wind forces drives magnetospheric dynamics, and he provided the statistical framework underpinning many modern analysis of the dayside magnetopause. So, yikes, a couple solar astronomers get asteroids named after them. And keep on going down and what? Yeah, okay, right there. Not the wrong one here. Charles Addams, the creator of the Addams Family and cartoonist, got an asteroid named after him. And the citation reads, Charles Addams, 1912 to 1988, was an American cartoonist who created the characters for the 1960s sitcom The Addams Family. His darkly humorous creations became a part of popular culture. This minor planet is the principal body and namesake of a small asteroid family identified by, oh God, I'm going to get this wrong, Nestorne and colleagues in 2024.
Nestorno.
Scroll down. This is one of my favorite Addams cartoons right there. Yep. I love that one. Death Ray Fiddlesticks. Why it doesn't even slow them up. And I was telling Brother Guy about this. And I wondered if Charles Addams ever did any picture of a telescope, and he did in the New Yorker. A giant telescope. The guy actually told me that this was right before the release of a major observatory. So that was in 1949. So that is the end of the solar and other report.
There is one thing a lot of people don't know, that you looked at temperature of 4,400 degrees Fahrenheit. The sun is about double that on the surface. So that object 4,400 is very cool.
Yep, that's why they call it ultra cool dwarf, which I didn't know was the.
I thought they were Game of Thrones.
All right. Thank you, Bob. Riyadh, what have we got for double stars?
Yeah, so at the last open house, we did look at some of the favorite ones like Alberio and Epsilon Lyra, the double-double. But we also looked at Izar, which is Epsilon Boötes, and that's a very nice looking double star. It's just under 3 arc seconds in separation. It's easy in the 8-inch refractor, as you can imagine, but it's a little bit of a challenge in a 3 or 4-inch refractor. Not very difficult, but it's nice to try to find the separation in smaller refractors with it. So we'll have another list of objects plus our favorite ones for the next open house as well.
Yeah, it was nice to see Izar. I hadn't looked at it in a real long time, and it's a cool double. All right, special interest groups. Is Tom Hagen here tonight? Radio? All right, I don't see radio, so we will move on to observing. Anybody got any observing done?
Oh, but I'm gonna have one for this next week.
Okay.
See the eclipse in Spain.
Hey,
Yeah,
Dave, I got something to talk about.
Excellent.
Not a huge deal. I don't sleep well, and I woke up about 3:30 a.m. this morning. I don't have anything to show. I just want to tell you. And I couldn't really go back to sleep. So what do? I look at my WISE cameras that are pointing north. I see a couple meteors right off the bat. And I went live on TikTok and saw about 13 in about an hour and a half.
Cool.
Wow.
And the other thing is make sure you got those pamphlets to pass out for the dwarf, right?
Yes, they are at the front of the table.
Excellent. Make sure you get one to get a discount before the price goes up, or the price would have actually gone up already. But check it out.
All right.
And that was it. Oh, wait, one more
That-
thing. I did just get a S30 Pro as well, so I'll be sharing some images from that soon.
Sounds cool. Any other observing reports? No? Okay. Then it is time for me to turn things over to Jonathan Cade to announce the speakers for tonight. I wonder who those could be.
It's gonna be a real boomerang kind of experience. Let's move this out of the way. Remind me to use the real mouse for this. Gosh darn it. All right, we have a presentation here. Sorry, I'm the AV person as well as the second vice president. All right, so now let's get this showing on the Zoom. What's going on? Oh, there we go. All right, now we are going to formally introduce things. Diane Hall is your president. She has previously presented to the club about locations as far as Estonia and Colorado and California and Hawaii. And tonight she's going to be focusing on things that I think you can all see from here. So as the song goes, to know her is to love her. Here is your president, Diane Hall.
Thank you. Hopefully I can reach the space bar. Okay. So tonight we're going to cover something back to the basics. 7 best things I personally have seen through a telescope. Now I'm not specifying an amateur telescope, but a telescope, not binoculars, not naked eye. It didn't work. Numero uno, the blue snowball, a planetary nebula, otherwise known as NGC 7662 or Caldwell 22, if you prefer the Caldwell calendar, Caldwell designation. So planetary nebulae are some of the most beautiful objects in the night sky if your eye is the size of the Hubble telescope. Cameras, especially cameras attached to school bus-sized telescopes, capture phenomenal images of delicate spirals and whorls and shells and antennae and all kinds of stuff. To the human eye, well, if you're William Herschel, you might see some green.
Go ahead.
Okay, so to our eyes, these remnants of dying sun-like stars appear ghostly. This is the Ring Nebula, aka M57, arguably the brightest and most famous planetary nebula. It looks like a smoke ring. Our eyes cannot capture its color. Our eyes cannot capture its structure beyond smoke ring. It's underwhelming. Planetary nebula are something I love to think about and don't really enjoy observing, except for the blue snowball, which actually boasts the blue-green Uranus-like color that lends planetary nebulae their name. The color perception varies from astronomer to astronomer. It's been seen as light blue, pale green, aquamarine, ever so slightly blue. Stephen J. O'Mara, probably the best visual astronomer alive, admitted that, even with his amazing eyes, he couldn't see a lot of color. Plenty of astronomers have, and I Got to see it in 2018 through the 40-inch Yerkes refractor in Lake Geneva, the largest refractor telescope on Earth. I could see.
Wait, you saw it through?
I saw the blue snowball through the Yerkes. I could see its structure. I could see the class O star at its heart. My mind was blown. I've never seen a nebula like that before. Will probably never see anything like that again. It was just mesmerizing. So you don't need the Yerkes to see it. The central star could be seen with allegedly a 16-inch telescope, which means it could be theoretically seen in the Big Dog. The internal structure can be seen even with an 8-inch telescope, so it's well within reach of an amateur, and it's located in the constellation Andromeda there. So totally recommended, great object, and the more magnification you get on that sucker, the better. Next. So I love globular clusters. I've done a whole talk about globular clusters. The thrill of turning my binoculars at a smudge of light or a pinpoint and revealing it to be a ball of stars never gets old. However, we're talking about telescopes, not my beloved Skymaster binoculars. Turning a high-powered telescope onto M5 in Serpents is pretty revelatory. M5 has exquisite structure. If this were a talk on binoculars, we'd be discussing M22 and Sagittarius. I love M22, but under high magnification, its structure is a little bit oblong and a little bit messy. M5 is exquisite. Chains of stars forming shapes like the petal of a lotus blossom. It is gorgeous. And if you don't take my word for it, Admiral Smythe, one of the great astronomers of the 19th century, calls it superb, noble, refreshing to the senses. Now, M5 is a little tricky to find. It's in the undistinguished constellation Serpens Caput, located roughly above the claw stars of Libra. It's not as easy to find as other bright globular clusters. You can find M4 easily, M13 easily, M22 easily, but it's worth the effort. It is a great, underrated object. Moving on to double star. Colored stars have always piqued my interest. I was the kind of kid who was into the Hertzsprung-Russell diagram, like into it. I even have a bracelet that I should have worn tonight that's a Hertzsprung-Russell bracelet. Double stars have always piqued my interest. Alberio offers both. Its appeal is pretty straightforward. Beta Cygni is a large yellow star with a smaller blue companion. That's it. It's colored stars. Ta-da! It's great. You can't beat it. Particularly if you have an association with the colors blue and yellow. I come from California. I think of it as the Cal Berkeley star. All of y'all here from Michigan can think of it as a U of M star. If you're an MSU person, I'm sorry, there's no green stars. You know, it's just not. We got blue and gold. Alberio is easy to spot during Michigan summers and autumns. It's the head star of Cygnus the Swan. Recently, it's been determined that instead of being a true binary star system, the blue and yellow stars just happen to be juxtaposed from our perspective. Oh, lucky us. But a little less interesting to think about because I had some ideas about that star system that, oops, it's not really a star system. Now, it is easy to take our moon for granted. It's there. Frequently, it's annoying us because we want a dark sky. I took the moon for granted until we acquired our first 10-inch telescope. Something about the view in that secondhand reflector blew me away. The highlands and the craters in the eyepiece seemed like I was looking out an airplane window 5 miles down. The moon is dynamic. Its face changes night to night as shadows expand and recede. It subtly changes month to month as it wobbles in space. I believe we just had a whole talk on lunar libration, which allows previously hidden areas to be glimpsed. It takes time and attention to capture its finest details, like the lunar X or the lunar V. Endymion crater can rarely be seen. The libration has to be just right. The straight wall is an effect that you have to time right. Crater Gassendi, again, not always visible. There's fabulous stuff that you have to be on top of it, catch the moon on the right night, and be rewarded. Also, depending on the telescope, you might actually see what appears to be some subtle color interplay, some blues and browns. You think the moon is gray, black, and white. Yeah, it is, but the guys who've actually been there, the Apollo crews, reported seeing some blues and browns with their own eyes as they traveled above the lunar surface. So, depending on how the sun hits, you might see some subtle colors. The first human to see the moon through a telescope was astounded by what magnification could do. Galileo thought the moon was about 65 Earth diameters away. He felt his telescope made the moon appear all of 2 diameters away. And he thought that was great, and frankly, I know the feeling. Now, when I finally acquired a telescope of my own in late 2006, the first item I wanted to see in it was the trapezium, the quartet of young stars inside the Orion Nebula. The Orion Nebula is swirls of glowing gas and dust encompassing a stellar nursery. It captured my imagination long before I owned a telescope. No matter how impressive the nebula was in my mind, the actual object exceeds expectations. And you think, what is that terrible photograph? That photograph was the first photograph ever taken of a nebula by Henry and Anna Draper in 1880. They took a better one in 1882. Then you can compare it with a modern photograph by Joe McBride, who some of us know from the Grand Rapids Club. Now, William Herschel, best visual astronomer of possibly all time, called it unformed fiery mist and noted that there's every variation of celestial doings: stars, multiple stars, blue stars, clusters, nebulae, gas, dust. It's got everything. Even if the human eye only sees a greenish glow instead of the multicolored swirls captured by photographs, the texture is superb. The complexity is superb. I've heard the Tarantula Nebula is even better. All I can say is I haven't seen it yet. We'll upgrade talk when I see Tarantula Nebula. Right now, Orion Nebula is tops. And I particularly have a fond memory of going down to the Hector J. Robinson Observatory owned by the Ford Club, and we were on a hunt for the E and F stars in the trapezium, because the trapezium actually has more than 4 stars. E and F are very challenging. I did manage to glimpse them. It was a cold winter night. It was so much fun. Great object. And it's easy to find. Wait till winter, locate the 3 stars at the belt of Orion, look for the fuzzy patch hanging out below. There it is. Now, I almost didn't include this one because it is a favorite binocular object. But double cluster, pair of open clusters in Perseus, unlike many open clusters, they stand up to high scrutiny in telescopes. The Pleiades, unless you have a wide field eyepiece, it can be a challenge. Beehive, same deal, other big open clusters. They're great binocular objects. They don't necessarily look so hot at high magnification. NGC 869 and NGC 884, they can withstand a lot. They are located 7,100 and 7,400 light years away, respectively. 869 is 5.6 million years old. 884 is 3.6 million years old. Chance alignment looks incredible. They're great at any magnification, so they are mind-blowing in binoculars, great in a small telescope, great in a large telescope. Bring it on, it will satisfy. Stephen J. O'Meara waxes poetic about it in his book on the Caldwell objects. I don't quite have his flights of fancy. Seriously, he could get a little bit out there. I think of them as a pair of snowballs, and I love it. They look like two snowballs hanging out side by side. Maybe this hostess snowballs in a cellophane package just waiting for me to eat them, but I love them. They're located in between Cassiopeia and Perseus. It can be seen naked eye in dark skies. It looks like a knot in the Milky Way. And easy peasy in binoculars, not a challenge at all. I'm going to be a contrarian when it comes to the best galaxy. I'm not going to cite the Whirlpool. Whirlpool's great. I'm not going to cite the Great Andromeda Galaxy. It's big. Not even going to cite the silver coin, though I thought about it. M33, or the Triangulum Galaxy, often called the pinwheel in older sources, is not as eye-popping as those other galaxies. It doesn't have the same surface brightness. What it does boast is the opportunity to see active nebula regions and globular clusters in another galaxy more than 2 million light years away, 2 billion light years away. It's got a lot. So in particular, NGC 588, 592, 595, and 604, active H2 regions can be seen in a 10-inch telescope or bigger. More you got firepower-wise, the better it's going to look. 604 in particular is often cited as looking brighter than the core of the actual galaxy. Apparently, it is not technically brighter, but it sure looks that way to a lot of observers. It just has so much going on. It's worth the effort to find it and to observe it in a true dark sky. It's a great naked eye challenge object, great binocular object, but if you've got the dark sky and you've got the telescope, you got to dig into it and you got to look for the nebulae. M33 can be found in our evening skies above and to the right of the point of Triangulum beneath Andromeda. And that concludes my favorite 7 telescope objects. Do we have any questions? I see a question from Jeff McLeod.
Just out of curiosity, if it was Gaia data that revealed that Albero's not a true binary?
Yes, it was Gaia data.
Yep. Do you happen to recall what distances which one's closer? No.
I just know that there was long-standing suspicion about it because at no point has the separation between the two stars ever been perceived to change, which it could be taking thousands of years, but it could just be happenstance. And Gaia concluded it was happenstance, and I'm a little sad, but not going to argue with that. Mike O'Dowd.
You saw
Yerkes, yeah.
How'd you pull that off?
I scanned my way in. I showed up right before they were scheduled to close when they had their shutdown when University of Chicago divested. And they had tours that were already booked up. And I forked over some cash. And there were 21 people on the tour that night. You can't do that now. They've got a new nonprofit running it, and but it was a very unusual time at the observatory.
You can go observe there.
Yeah, but you can't just it's not panic time anymore. It was panic time that week because they were literally days from shutting down. Any other questions?
Got a question.
Yes, Ken.
Explain a little bit with people about what actually a ring nebula is.
They're just so when a sun-like star dies, it swells up into a red giant, and as it dies, it puffs out its outer layers that form concentric shells.
And our sun is going to be that.
That is how our sun will die. Our sun will not go supernova. So all of these beautiful, what they call planetary nebulae, are sun-like stars that have gone kaput.
Thanks.
Any other questions? All right. Well, thank you very much.
You're in charge again.
Well,
Oh, yeah.
he's leaving as presenter now, he's coming.
Oh, yeah. So that was me changing the hats. It's now snack time. We've got snacks courtesy of kind people who brought excess to the picnic and moi. And we've got water. So we'll take 15 minutes to enjoy.
Thanks for not overlooking the bill.
Yes, it had to include it's phenomenal.
That,
Yeah.
You're going to resume in 15 minutes at 5 minutes after with the feature presentation.
Rick Bell did a presentation on you were getting a double like down in the last 15 solar cycle does have a double. Are we going into the second double then or I'll be find out. Curious. So I'm gonna find out it seems worrying back on and he's worried going to double play. So all this activity, like just in the games being no, yeah, and yeah. You know how we post that thing in the newsletter from AstroPixels? The sky phenomenon for the month. Newsletter? Yeah, the newsletter. We do it on the website. No, it's in the newsletter. You can copy something from AstroPixels.
Maybe if we're lucky, Bob Tremblay will come tell us what this is. Test check test.
But
Test check test.
brother,
Test check
we have
test.
this astro photo calendar.
I have published records, right?
And brother guy,
Test check test.
development record. I want you guys to go through and make sure everything in the calendar is correct. And oh my God, things are freaking best. There were things in there from 2 years ago that,
Maybe if we're lucky, Bob Tremblay will tell us what this is here.
things after in the stuff. Some of the dates were actually it's just generally sure. Dates were like the U.S. Naval Observatory. So I go to the U.S. Naval Observatory and can't find resolution maps and what up some calendar events. Yeah. Oh, yeah. Yeah. From supposed to be grabbed from astrophysics. I was looking at it.
So this is a new photo from the JWS team.
Joining
Helix Nebula, a small portion of the Helix Nebula from the JWS
Membership now.
into it.
When will it take effect?
Crazy. Thunders of gas and dust, all pointing
Zero.
central white
From
dwarf.
here. So they would wait until the next July for it to kick in. But I was in conversation or email conversation with some of our experts, and they will do a pro rate. So we need to find what the pro rate of prices, and then we could get you on. Yeah, I'll talk to Astronomical League and see what we can do about all of that. And we might owe you the money back. Could be prorated. Yeah. Oh, okay. Oh, okay. RJJ. Thank you.
Thank you.
We're on the red line. So it's. That goes to Dale. What is this? What is it? That's our. What are, this is. Can't start to get like that, and you and the citizen stuff. Yeah.
What?
Are you the treasurer?
Yeah.
So I don't, we haven't hardly been up to date in a little while. It's Kevin McLaughlin, so.
Want to join?
Yeah, sure.
How old are you?
I'm 67.
I'm a senior.
But would you have my information in it already, or could I have to?
Definitely.
Yeah.
You remember before.
Yeah, Kevin McLaughlin.
So it's $22.
Yeah, sure. Is that okay?
Yeah. Kevin.
Yep.
Rockland.
Yep. That's C, L, A, U, C, H, L, I, C.
Can somebody who is on the Zoom call say something? Hey, it's kind of working.
Sounds good.
Can you hear me now?
I can hear you.
Yes, we can. All right. How's that? Gary, can you see those? All right.
Oh,
Yeah.
The transcription is maybe not the best, but it's better than nothing.
This was sent out well before. I think we're okay. And but we might want to call telephone and find out. No, it was I have one.
Yeah, I wonder if we can use that. Look, it's picking up next here.
May I ask, is anyone on the call right now or presenter for tonight?
What?
Hi, is Professor Maitra on the call?
It's.
This is the,
Professor Mitra on the call.
no, this is the us, this is our transcription.
Oh.
Our very poor transcription. We are trying to locate our presenter.
Is there a way to see the TV? No. Doesn't prison. Depending on some up. Oh, really? Oh, there he is.
All right. Our presenter is here with us tonight. Everyone, if could find your seats again. Diane, do you want to introduce me to?
All right, ladies and gents and friends, let's take your seats. It is time for Jonathan Cade to introduce our featured presenter for the night. Take it away, Jonathan.
All right, thank you. Our professor tonight, our presenter tonight is Professor Dipankar Maitra. He is an astrophysicist by training and an amateur astronomer by heart. He works with students and collaborators around the world on understanding what happens around black holes and neutron stars. He's especially interested in understanding the coupling between accretion inflows, stuff being added to massive bodies, and relativistic outflows near those objects, the hair coming off of them. Lately, he's been interested in optical polarization studies of the solar corona and other astronomical bodies as well. He's constantly searching for better ways to involve students and amateur astronomers in performing astronomical research and making physics and astronomy more welcoming and inclusive for everyone. He's an astronomer at Wheaton College in Massachusetts and uses telescopes in Wheaton's on-campus observatory and ground-based remote observatories across the globe, as well as space-based telescopes. He also has a history here in Michigan. So thank you, Professor Maitra, for being with us, and take it away.
Awesome. Can you guys hear me?
Sorry, go ahead.
Can you guys hear me? Okay.
Yes, yeah, we can hear you great.
All right, let me start sharing my screen. So hopefully it'll work. Let's see. Application windows. Chrome. Okay, let's see. Open system settings. Hold on, sorry, this is technical giving some issues. All right. And let's see. All right. Allow, hopefully that will allow. So are you able to see my presentation screen now?
Yes, we're seeing the actual PowerPoint window rather than the presentation window. But
Yeah, hopefully if I hit the slideshow, is it working
yep,
now?
looks good. Yes,
Good.
thank you.
All right, perfect. Okay, folks, let me get started. Thank you, first of all, for inviting me to give the talk. Thanks, Jonathan, for the nice introduction. I will talk more today about variable stars, although I will touch a little bit upon on my work on black holes that we can actually do with small telescopes. Um, so um, so jumping into the talk, so my goal here is to hopefully show a few cases of how variable stars are useful to astronomy and how they can help understanding the universe. So, you ask most people, people will say that, oh, the skies are nice, vast, constant, nothing ever changes in the sky, right? That's the common perception. However, if you look a little more carefully, that is not true. The skies are in fact quite dynamic and restless. If I can show this video taken by my friend Walt Cooney. Here you can see at the center a star that even the other stars don't change in brightness at all, and this one almost disappears and comes back again. So this is actually an eclipsing binary, a star that gets hidden behind the other one. It's DQ Hercules. It's actually up in summer skies right now. And if you see on the right side here, this is what we astronomers call the light curve, this graph over here, which shows how the brightness changes with time. And here's Walt's data, his measurements from the video, actually from the images that he took. The y-axis here is magnitudes, which I assume most of you are familiar with, the famous inverted scale of brightness. Smaller numbers are brighter, and going up by one magnitude is actually getting almost 2.5 times brighter. So here this star DQ Hercules, which is most of the time at around a magnitude of 14.5 or so, every 4.6 hours, it drops by almost more than 4 magnitudes down to below 17th magnitude. That's basically what you were seeing in the video over here where it, disappeared. That's like getting below the detection limit of Walt's telescope and coming back again. So that's to me like pretty crazy, and only within 4.5 hours. What's going on? Well, it turns out variability happens in the skies on all kinds of time scales, all the way from milliseconds to years. Here actually is data from an 8-meter telescope looking into the pulsar that lives at the very center of the Crab Nebula. This is the remnant of the supernova that exploded in 1054 AD. And we all have probably seen this expanding shell of supernova ejecta. But the neutron star that is left in the very center, as it spins, as its magnetic poles sweep past us, we see brightness jumps. That's actually that entire a sun-like object rotating every 33 milliseconds. So every 33 milliseconds, you see a spike. This spike was first noted in radio, but since then, as instruments have gotten better, you can see it. If you have an 8-meter telescope and something that a camera or a video camera that can get to milliseconds, you can see the Crab pulsar flickering. So that's on the short time scale. On the other hand, here is the variable star Myra or Omicron Ceti. Here's data from the American Association of Variable Star Observers, which goes back more than 100 years. I've only shown the last few years, or last, from 1950s through 2010. You can see its brightness changing from sometimes gets up to third magnitude or so quite easily visible with naked eyes. But at its faintest, it can get down to 10th magnitude, so it's even difficult to see with a binoculars. You'll really need a telescope to see it. And even though the exact cycle changes a little bit, it roughly repeats every 332 or so days. Here's another example of a star, GK Persei. It's a recurrent nova. It's basically you have a white dwarf orbiting another sun-like star, and material from the other star is falling onto the surface of the white dwarf, and that accreted material gets hot, and as you're dumping material on it, the surface of the accreted material on the surface of the white dwarf gets very hot, and once every few decades or so, as you can see from these light curves, um, once in a while, this entire skin of the white dwarf, the accreted hydrogen, just burns off as a huge hydrogen bomb over a span of few weeks, and then it goes back to normal. So this is an example of a variable star doing things on scales of decades, perhaps, or years. So the toolkit here for variable star astronomers, what we measure, we call it photometry, right? Metry is for measuring, and photos is photons, the brightness of light. So what we measure really from the Earth is the apparent brightness, how it appears as to us. We try to do that as accurately and precisely as possible. Um, Usually the way it's done, especially for optical or visible light telescopes, is we compare the brightness of the star, of your target star, with some nearby comparison stars. And of course, you need to note down, when you observed it, what was its brightness, and where you are, because sometimes that can be important too. So what tools do we use? Well, going back and even now, visual photometry still remains quite useful. Um, People often, trained observers, can look at the skies with their telescopes or even binoculars and can determine the brightness of their target, sometimes down to accurately within a tenth of a magnitude. Here's a picture of an Indian amateur astronomer. He never passed high school, but he contributed more than 50,000 visual observations to the American Association of Variable Star Observers, or AVSO, during the first half of the 20th century. He initially he put together a small 3-inch refracting telescope, but his data quality was so good that AVSO later sent him a 6-inch refractor, which you can see here. But the tradition continues, and especially for very bright targets, right now, most detectors will saturate. So, eye still remains, visual observations with your eyes still remains a very important way of contributing data. However, with the progress of technology, oh, by the way, before I get to technology, I should show, like, this is what we call a finder chart. So here's the star, SS Cygni, let's say, which would be here. And these charts prepared by AVSO contains a whole bunch of reference stars, and their brightnesses are noted here to the first decimal, like 109 means 10.9. 77 means 7.7, and so on. And so by comparing your star's brightness with respect to these comparison stars, you determine how bright your target star is when you are observing. The same process, whether you're doing visually, you do this in your head, or nowadays, with technology, if you use your digital SLR camera or a CCD or a CMOS camera, you have dedicated software to do that. So in terms of modern day, you can have even a small telescope like this, which is tracking the skies, and with a camera attached to it, can get you very precise data. More and more common are becoming these smart telescopes. Here's a C-Star S50. You can basically put it out in your backyard, with very little fiddling, it'll start sending you data to your smartphone that you can later analyze. And of course, while these are perfectly fine, I wouldn't complain if you build an observatory like this either. This is as you can see, This is actually Dr. Mario Mota. He was the president of AVSO a while ago. He built a 32-inch telescope in his home, and no complaints about that. But you can do things with lot smaller telescopes as well. So moving on, why does it matter? Why would we like to observe variable stars? That's because variability reveals what physical mechanisms are going on. And I'll show you a couple of examples how variability reveals what's going on. It bridges the gap between theory and observation. Of course, theorists have all their models in their head, and then they translate them into numbers and make predictions and say that, oh, if this is what is going on, you should see this. But then it's up to the observers who have to go and look at the skies, make the observations, and see if what you observe is what the theorists have predicted. Otherwise, you are fine. Observers are always correct as long as you work with your data honestly, right? It's the theorist who has to go back to their desks or wherever they're working their theory. And as I will soon show, variability is something that impacts almost every subfield in astronomy. Examples like exoplanets, stellar structure, galaxies, even cosmology depends on measuring variable stars. So let me show you a view graph, almost a zoo of what kinds of variability we see in the skies. And you can see that things are not just limited to stars. Asteroids can show variability. Stars obviously can show variability. Even accreting black holes can show variability within human timescales. So in this nice view graph, the authors have split various kinds of variability into myriads of small subfields of variability. I cannot claim to know many of these. If you ask me about, oh, what is one particular, what are the, I'll have to probably look them up as well. But just to give you a broad overview of what variability typically can mean in astronomy. So of course, I don't have the time or energy or the knowledge even to go through each of these, but I'll just start you off by saying that mainly variability that we see from the skies can be split in two different ways, or two different broad baskets, if you wish. There are extrinsic variables in which variability is caused by properties like the rotation of the object or how the object is shaped, like asteroids. If they are very potato shaped, depending on which side of the potato is facing you, you will see it brighter or fainter. Or some stars, they can get tidally distorted if they are close to another star, or if they're near falling into a black hole. Their shapes get so elongated that depending on which side you are seeing, you can see different brightness. As they rotate, their brightness can vary. But these are extrinsic in the sense that they are not really caused by changes in the physical properties. So that brings me to the other part of variability is intrinsic variables, where the variability is caused by the object itself doing something. It could be pulsating, it could be expanding, contracting, like breathing, or like that recurrent nova that I showed you earlier, GK Persei. It could be erupting. It could erupt once, or it could erupt every so often. Some of these systems, we call them cataclysmic variables. These are ones where material builds up in an accretion disk before it falls in a whoosh in a very short amount of time. So it takes some time for the accretion disk to build up. And while that happens, the system looks quite faint. But then something triggers, and then all the material stored in the disk uh, quickly falls into whatever it's falling in. Could be a white dwarf, could be a black hole, could be a neutron star. But those things cause the brightness to increase very rapidly within a very small amount of time. And of course, then you have your stellar explosions like nova, supernovae, gamma ray burst, and so on. We call all these under intrinsic because the star or the object itself is doing something. Here's an example of what you can do by observing an asteroid. This is an asteroid Penelope, also numbered 201 in the Minor Planet Catalog. If you observe it over the course of the night, and this is actually not very faint, this most of the time hovers around 10th or 11th magnitude. So yes, you need a telescope, but nothing too fancy. But if you looked carefully over the course of the night, again, in about 3.75 hours or so, you can see the light fluctuating, one small peak and then another larger peak. And the peak to peak brightness, the maximum brightness change can be about 0.4 magnitude or so. So then you submit that data to theorists who are modeling these light curves. And from light curve modeling, they have come up, for example, for Penelope, this is the 3D model they have come up with. This is the same object shown from three different, viewing angles. So this technique is called light curve inversion technique. And these folks at the Astronomical Institute at Prague, they're experts on doing that. So they would really love your data on asteroids if you like tracking asteroids and their brightness changes. Another thing with asteroids, of course, is also you can actually see their position change throughout the course of the night. And you can, in fact, contribute those position changes and help to refine the orbits of the asteroids as well. So lots of things you can do with asteroids. I believe Calais Talk from AVSO gave a talk to you guys maybe a few months ago or so about what you can do with exoplanets, right? So this is where a planet orbits its host star, and in the process of orbiting its host star, once in a while, it blocks some light from the host star because the orbit is inclined in such a way that every so often it kind of eclipses the star, except that the exoplanet is very, very small. So instead of a full eclipse, you see a tiny drop in brightness of the star. Many of you will remember things like the transits of Mercury or Venus that have happened earlier this century. Essentially the same phenomena happening hundreds of light years away. Once again, you can do this if you know which star to look at. You can use even small 4, 6, 8-inch telescopes to get good data on their brightnesses. And here's one such light curve showing, before no change in the brightness of the host star up until this point, and then as the planet starts going in front of the star, it starts blocking the light. And here at mid eclipse, it blocks most of the light, and then the star, recovers its light. Of course, you have to measure light very precisely, as you can see here from the y-axis. The light dims by only a few percent or so. But once again, you have the tools these days to measure this kind of a few percent change in brightness, even with small telescopes. And using data like this, nowadays, again, the great folks from Exoplanet Watch, led by Bob Zellum and others, they have written very easy to use software that you can feed your light curve data and get physical properties like the ratio of the radius of the planet to the radius of the star. In this case, it was measured to a very high degree of accuracy. Like the uncertainty is of the order of 1 in the last decimal place here. And this I is the inclination of the orbit of the exoplanet with respect to our plane of sky. That's also measured very precisely from observations. So your observations can help refining orbits of exoplanets. Another example that I'll spend a bit of time on is pulsating stars. And especially this is one of our poster childs, the star called Delta Cepheid, the fourth brightest star in the constellation of Cepheus. And if you look at it carefully, you will find that the brightness or apparent magnitude of Delta Cepheid varies between 3.6 to 4.3 over the duration of about 5.4 days. So it's like clockwork. It's a rapid rise and then slow decline and then again a rapid rise and so on. And it keeps doing that. The star pulses like heartbeat every 5.4 seconds. So what's the astrophysics? What is going on here? What we have figured out is that in these pulsating stars, the variability is largely caused by changes in opacity due to the helium that's present in the star. Delta Cepheid is one example. There are other pulsating stars like RR Lyrae, Delta Scuti, and so on. They have different variability periods, but largely their physical mechanism of pulsation is something like this. So let's imagine that this is the star, and most stars, their surfaces are actually not hot enough for helium to be ionized. So for those of you not familiar with a helium atom, I put a little cartoon of a helium atom. It has 2 protons, 2 neutrons, and 2 electrons going around it. And if you put this helium atom in hotter and hotter temperatures, the energy of that temperature, the energy related to that temperature can kick off one or more of these electrons and make it ionized. So as I was saying, most stars, their photospheres, the outer surface, is not hot enough for helium to be fully to be ionized. So helium is neutral on the surface. But if you could go towards the interior of the star, you will soon encounter hotter temperatures where helium is singly ionized. Like it's hot enough that one of these electrons has been knocked out, but the other one is still there. You actually need even higher temperatures to knock that second one out as well. So let's see how it works in these stars, how pulsations happen in these stars. So as the star contracts, the density and temperature of the ionized helium layer, which is here in the interior, the ionized helium layer's temperature increases. The increased energy in that ionized helium layer now can knock out the only remaining electron that was there in this layer. That electron can also get knocked out. So you are left with a helium atom that is doubly ionized, essentially no electrons remaining. Some people may also call it an alpha particle because that's what a bare helium nucleus is called. So this is where we are in the stage of the star. The star has contracted. This layer has gotten hotter. The helium has become, most of the singly ionized helium has become doubly ionized helium. But where do these electrons go? These electrons can't just escape. They stay in this layer as well. And it turns out that free electrons, like now all these helium atoms that were there, all their electrons have been liberated from them, and all those electrons are freely floating around in this layer. And these increased free electrons are very good in absorbing all the light, all the energy that is coming out from the interior of the star. So the increased number of free electrons in this layer cause the radiation from the interior of the star to be largely absorbed. In other words, you can think of it that the star now has become opaque. It's not allowing the energy to come out. But when you don't allow energy to come out, it's like the star has become like a pressure cooker. It gets hotter. So the trapped energy inside that layer, in the star itself now, causes the star to expand. Thankfully, our pressure cookers don't usually expand. If they did, that would be an accident. But in the stars, there is no such strong handle to keep the pressure confined. So now in that opaque star where the trapped energy and pressure increases, the star becomes bigger. As it gets bigger, as the star expands, the temperature cools. As the temperature cools, now those doubly ionized helium nuclei can recombine. Basically, they can take one of those freely floating electrons and form back a singly ionized helium. And once you do that, then this layer, which now becomes again largely singly ionized helium, has become much more transparent. This allows the energy that was trapped to escape out. And when you have enough of that energy radiates away, that layer again becomes cool enough that it can start contracting again. So we have basically created this cycle of pulsations. Essentially, the star is breathing. Sometimes it's, expands and then cools down and contracts and becomes dense and expands. And this cycle goes on. And that's what is going on in these stars like Delta Cephei, RR Lyrae, Delta Scuti, and so on. But sorry, was there a question? Sorry, I couldn't hear you. Okay, I'm assuming no questions, so I'll go ahead. But if you do have questions, please feel free to interrupt, and we can have a questions. So anyway, moving on. Nowadays we know all of this is going on, but when they were first discovered, none of this was known. It was all, as we say, empirical. The evidences were empirical. And one of the first few people to look at these Cepheids very carefully was Henrietta Leavitt. At the turn of the 20th century, she was working at Harvard College Observatory, and they had images of the southern sky, especially southern small Magellanic Cloud, was observed very carefully using Harvard's telescopes in the southern hemisphere. And she saw that, firstly, she found Cepheid variables in the small Magellanic Cloud, but then she actually noticed that these Cepheids had a very interesting relationship. Not all Cepheids had the same period of oscillation. Like Delta Cephei oscillates every 5.4 days. But there are other Cepheids which oscillate with longer or shorter periods. And what Leavitt found out was that the period is correlated with the luminosity of the Cepheid, that is, how bright the Cepheid is. More luminous, brighter Cepheids took more time to oscillate, whereas less luminous Cepheids oscillated much more rapidly. That actually was revolutionary in some sense, because that now allowed us to treat these Cepheid variables as standard, what we call standard candles, or like stars whose brightnesses we know. And if you know the brightness of a star, then you can find out how far away the star is by looking at how bright it appears. It's just like, look at all the street lights on your street. They all hopefully have the same bulbs, the same wattage, the same luminosity. But obviously the nearby ones appear brighter, whereas the ones that are farther and farther away, their brightness diminishes as the square of their distance. So if you know how bright they are, and if you know how bright they appear, you can figure out how far away they are. And this is exactly what Edwin Hubble did. Is first of all, when he was starting off, there was even a big debate about the size of the universe, and people thought that our Milky Way is all there is in the universe. And these nebulas like the Andromeda, they thought they were gaseous objects within our Milky Way. But what Edwin Hubble could do, thanks to the fact that he also had access to the largest telescope that was around at that time, uh, Hubble actually found Cepheid variables within the Andromeda Nebula. And then he applied Leavitt's period luminosity relationship and figured out how far away Andromeda Nebula, the Andromeda Nebula, which we now call the Andromeda Galaxy, is. So Hubble was the first one to prove that the Andromeda is a separate galaxy, and thereby he suddenly increased the size of our known universe at that time by quite a few. Actually, Hubble didn't stop there. He went on and found Cepheids in other nearby galaxies, out to galaxies that were 50, 60 million light years away. And using those, he had to do some spectroscopy as well, but he could put together the distance information from Cepheids and the velocity information from spectroscopy. And he discovered that we actually live in a universe that is expanding. So this is just to show that, how measuring brightnesses of variable stars led to measuring the scale of the universe. Let's fast forward another 100 or so years from Hubble. I wanted to sort of, end by saying what you can do with a small telescope. Here's, a black hole binary system called V404 Cygni. It's, as the name implies, it's in the Cygnus constellation. What this obviously is an artist's impression here. What we think is going on, we think there is a donor star of mass somewhere around half to one solar mass orbiting another black hole which sits right at the center here. The black hole has a mass somewhere between 10 to 15 solar masses. And as the donor star goes through its life cycle and it's on its way towards becoming a red giant, material from the donor star gets captured by the gravitational field of the black hole. This accreted material swirls around in an accretion disk and eventually falls onto the black hole. So this particular system, V404 Cygni, it went into an outburst, which means like if you look at it in like Cygnus is up up in the skies right now. So, and if you look at V404 Cygni, you will find it at a brightness of about, I think 18 point something magnitude, visual magnitude. But in 2015, around in late June of 2015, it brightened up suddenly to like 12th magnitude. So even with small telescopes, you could see it. It actually went into outburst prior to 2015. I think it went into outburst once in 1989. and then also, I believe, in the 60s or so. But of course, the 2015 outburst, thanks again to advances in technology, people, astronomers, professional and amateur, all across the world, turned their telescopes and looked at it at every possible wavelength. We had radio telescopes looking at it, microwave telescopes, millimeter, infrared, optical, X-ray telescopes, gamma ray telescopes. Everyone was looking at V404 Cygni because it was actually doing something at all these wavelengths. So since it was doing all this crazy stuff, we decided, I actually had an undergraduate student at that time doing a summer project with me on something completely unrelated. His name is John Scarpacci, and I told him, John, stop whatever you're doing and let's try to look at V404 as well. So here's on our observatory roof. You see here John very formally dressed, using a trash bin, inverted trash bin to put his laptop. Um, and he put a cardboard box so that the glare from the laptop will not, cause problem to the telescope's light gathering. Of course, this is staged in the evening when we were taking flats. But here's the telescope we used. It's a 12-inch Meade telescope attached with a CCD camera. We got extremely lucky. This was right around new moon. And very surprisingly for New England weather, we had a very clear, at least 2 clear nights. And we made good use of both of those nights. So I'll show you data from one of those nights. This is the second night. The first night we were not sure what would happen, so we just used a green filter that we call a V filter and observed it continuously in that one single filter in like greenish light. And we got 450 or so images throughout the course of the night. And we got some good data out of that as well. But then we got bolder on the second night, and we decided that we will observe not just in green, but in red and slightly infrared as well. So these are our light curves in all those 3 different filters. Throughout the course of the night, you can see that in the beginning half of the night, it was doing these crazy things with brightness jumping by a factor of, more than 100 in few minutes. Actually, this last drop here happened right around midnight our time, and I could really see it disappear from our CCD images. And I was yelling at John, increase the exposure time so that we don't lose it. So you see the data is more closely spaced here and a lot more spaced out here. Later on, one of my friends said, oh, the Integral, which is European Space Agency's X-ray telescope, the Integral was also observing exactly at that time. Why don't you look at what Integral saw as well? So when we were working on our paper, we included the Integral data as well, which is shown here in black. And you can see the same kind of variability in both the Integral and the optical data. It looks like just ups and downs, but it took us 2 years to analyze this as carefully as we could. And in fact, the data was so good enough that we could actually put together a story of what was going on. And we managed to even publish a paper in the Astrophysical Journal, one of the most prestigious peer-reviewed journals in astronomy. And what we basically convinced ourselves, as well as the referees of the paper, is what is highlighted in our paper's abstract here, that the variability we saw, we think, was not created by light produced by fusion in a star, not produced by light that was falling towards the black hole, but instead by some small fraction of material that was somehow ejected by the black hole perhaps at speeds close to the speed of light. Later on, my friends who observed also using radio, they saw not exactly during these same times, but a few days before and after, in radio, they could actually see blobs that were moving near the speed of light as well. So just to show that, you can do with small telescopes very interesting stuff as well. Of course, a bit of luck is involved. I haven't had a chance to repeat this in the last 10 or so years, but I'm waiting. So, what can we do? There are way too many stars and far too few what you might call professional astronomers. And the problem is that, these professional telescopes in professional observatories, they have only very limited time, very limited flexibility. Most professional telescopes won't be able to image once something gets really bright above like 13th, 14th magnitude. Their schedules are inflexible. They want to do things and their schedules are decided like 6 months, a year in advance. And they really, really hate changing their schedule. So, asking for time on a professional telescope for something like this, something unexpected, is very unlikely to happen. And also, depending on what you're looking at, oftentimes professional telescopes will have very narrow field of view, and that may not be of interest to you. Some people, will say, oh, but these large survey telescopes like the Vera Rubin, the LSST, they'll do everything for us, and amateurs will have nothing else to do. Actually, first of all, telescopes like the Rubin telescope, LSST, it will generate lots of alerts, but it cannot really follow up very effectively. It will take some time for Rubin to come back to that same star again. Whereas if you are a citizen scientist, if you're an amateur astronomer, you can go and dedicate as much time as you want to that target. Also, telescopes will, like Rubin, will get saturated at 16th, 17th magnitude. So all the brighter stuff needs to be observed. The data from citizen astronomers is vital and is often superb quality. They can provide continuous coverage that professionals can't do. Professional telescopes will only observe once and not again. You can do it one whole night. If you have friends across the globe, you can basically follow the target all around for 24 hours if you can. You also, if you get really interested in one such target, you can observe it for decades. I actually was looking at some data of some of these binaries recently with another student. This was again material being dumped on a white dwarf from another binary companion. And this dumped material causes the spin of the white dwarf to change. But if you look at data spanning like decades, you can figure out hundredth or thousandth of a second change in the orbital period of the white dwarf. So long-term data is very valuable, and this is where citizen astronomers can be, really provide really useful data. Things like rapid alerts, something is going on, who can observe? We often, when I work with the American Association of Variable Star Observers, or AVSO, we send out alerts that something is happening, please observe. And we get lots and lots of people contributing excellent data. And as I was saying, these bright stars, which big telescopes can't look at. These data, the data that you will take and contribute, has enormous historical legacy value. Like I was saying, that we were looking at older data of white dwarfs, and only by looking at decades of data can you figure out, how fast or slow a white dwarf might be spinning up or spinning down. Now you might say, oh, that might need very crucial gear. Well, actually, if you are somebody who does astrophotography, you actually, most likely, your hardware is fully capable of doing very precise photometry. You may not do it yet, but you have the capability. If you spent 8 hours looking at a nebula taking 30-second subs, each of those subs you can likely find within the field of view of each of those subs there probably are few interesting binary stars, or not binary but other variable stars. And if it took you 8 hours or however many hours, you can create a light curve and submit that data. The modern digital detectors like the digital SLR cameras or CMOS or CCDs, they capture great data. I mean, this is the newer CCDs and CMOSs are better in terms of their quantum efficiency than professional gears were even 10 years ago. And with small backyard telescopes, even if it's a 4 to 14 inch, anywhere there you can get really good data. You can do lots of science with that, and you don't have to again stay awake the whole night. Nowadays you can tell, even with a smart telescope like C star, you can plan your observations and go to bed, and the C star will take your data, and next morning, hopefully if it didn't rain, you'll get excellent data. So I think I'm running out of time here, so I'll stop here and stop sharing and take questions.
Any questions?
It's Seppi, not
I-
star.
I have a question about the V404 system. How did a sun-like star come to orbit a black hole? Was that the remnant of a supernova, or was it captured by it?
If you're talking about the origin of how that binary system got created, that's a very good question, and we don't know where, how it began, but more likely rather than capture it, I would bet my money on the fact on the suppose probability of both being created at the same time from the same large cloud, like most binaries are created. It's just that one was created much more massive, which went through its life cycle much faster, exploded as a binary, and the other one was less massive and evolved much more slowly. What is super rare about this is that a supernova explosion creates huge amounts of energy,
Right.
and
Yeah.
and very often that supernova explosion would unbind the system, and they would go flying apart. But we have found over actually like hundreds of X-ray binaries where you have a supernova remnant orbiting a late type main sequence star. And we think most of them are, they originated from the same time, at the same time. Does that answer your question?
Yes. Thank you. Any other questions? Mike?
What is the nearest classical novi to the Earth in distance?
Could you hear that?
I'm sorry, could you repeat the question, or maybe,
The question
yeah.
was, what's the nearest classical nova to the Earth in distance?
Excellent question. I don't have the answer to the top of my head. Also, the distances are only recently being measured. I would say that, like for V404 Cygni, actually, my friend James Miller Jones, he was able to measure the parallax of this system using radio interferometry, and so we know its distance to be reasonably precise, of the order of like 1.3 kiloparsecs or so. That's about 3,500 or 4,000 light years. The Cygnus X1 system, I think, is again in that same kiloparsec or again few thousand light year regime. Um, I don't think we know of any such system that is perhaps within a few hundred light years. And maybe that's for good because if these things are too close, that can be a problem in its own.
Yeah, the last closest nova to the Earth currently is T Corona Borealis,
Okay, T Corona Borealis. I've heard that.
which is expected to erupt in the near future, although the exact timing is uncertain.
Absolutely. Thanks for bringing that up. I was hoping to talk a bit about T-Core Bor, as you may have heard from many folks that we are, at least the predictions by Brad Schaefer are almost a little past overdue. He
Yes.
said like 80 or so years. So any day, any time, it can go off. I'm not 100% sure on what if there's a solid distance measurement to it. But yeah, it would be fantastic when T-Core goes off. One more reason to do variable star to get into variable stars. Yes, please go ahead.
Yeah, the object jet that you caught for your publication, were you just lucky, you said, or were you looking at a specific candidate that you thought may eject a jet?
No, we actually, so it was first detected by the Swift satellite, which has an all sky, high energy all sky camera, and they detected excess of high energy coming from that direction. So they sent out an alert, which we call an astronomer's telegram, by the way, which is a website. You can just go to astronomerstelegram.org. And that's how the rest of the world came to know about it. And we looked at it as soon as our New England skies cleared up.
So what I think Ken was asking also, because it's in your research focus, were you particularly interested in that, or did it just seem really cool?
It's in my research field, but the truth is, like, it last erupted in 1989 or so. So we were not, and there was even another previous explosion, but there is no regular periodicity in most of these X-ray binaries. I have had many friends, lose money on bets saying, "Oh, this is going to explode now," and then nothing happens. In fact, that was the topic of my PhD thesis is what triggers a particular X-ray binary to go off and become and start doing crazy things. And luckily or unluckily, that problem is still unsolved. So no, we were not hoping for that, but anytime one of those goes off is a big boon for us.
Yes, Mark.
Yes. Are you active with the AADSO right now?
Yes.
This time? Okay. I don't know if you've heard the name Mike Simonson. He passed away about 10 years ago. If you see all those finder charts for looking for variables, he was a prolific variable star observer here. He was our former club president, and
Oh,
he had a big thing with designing the star charts for the type of telescope that you're using. So it would aid this, amateur astronomers to get into, observing variables. He also had this thing where he called it a campaign. His favorites were cataclysmic variables. He loved them. So if something was shaking up in the skies, he would send out that alert, and
mhm.
he'd create a campaign to have everybody start looking at that and get those measurements and everything that he needed. He was quite the guy when it come to variable star. Learned a lot from him.
Thank you for no, I mean, I didn't know him personally, but I mean, that's a wonderful thing that was done there. Like this, the creation of the Finder charts is such an easy thing nowadays. You just go to the AVSO webpage and you can, customize things a little bit here and there. And there you have your Finder charts. And if he's the one who started those AVSO alerts, we still use them to great effectiveness. So yeah, no, thank you for mentioning that.
Yeah, he was the development director for the AVSO too, so he got a lot of funding for them over the years. Any other?
There's a question out there.
Oh yeah, Greg, would you like to share your question? You can come on or put it in text.
Yeah, I have a question. How do you study, what's the best way to study, say, a pulsar? You know, when it's issuing in its rotation all that magnetic energy. What is the best way they observe that?
Um, I mean, traditionally, and still most pulsars are studied in the radio. That's where, it's easiest to detect them. Now, but that said, as technology improves, like I showed in my first slide, they didn't pursue it a whole lot. But if you have a huge, big enough mirror and a fast enough camera, you can detect pulsations from a pulsar even in optical, or even the Chandra X-ray telescope, which operates in X-rays, has detected pulsations from the Crab pulsar. Um, I would say that actually the optical, unfortunately, is not the most suited. A lot of pulsar studies are done either in radio or in X-rays, and that has to do with the emission mechanisms and where most of the energy produced by them is concentrated.
Okay, thanks.
Yeah.
I have one last short question. So as somebody who thus far, we have a member, Dave Noble, who has been a very strong evangelist for sea stars and this Dwarf Labs telescope that they actually donated to the club, and we've been circulating among our membership. But we were wondering if you don't have one of those astrometric devices, uh, what can visual only observers best contribute to at this point?
Again, depending on the size of the telescope you have, you can look at fainter and fainter stars even visually. What I know, for instance, is there are people who can do with 6-7 inch class telescopes under reasonably dark skies. Just with their eyes, they might be able to do up to 10th or 11th magnitude stars down to 0.1 magnitude, roughly, uncertainty. It requires practice. Some of my mentors back when I was in middle school, um, they they used to live in the cosmopolitan city of Calcutta in India, and so enormous light pollution. But with their 9-inch telescope, they contributed data to AVSO, um, good quality data, which means I'm guessing, I'm not 100% sure here, but the uncertainties were less than 10th of a magnitude. But I doubt they from a big city like Calcutta they could go below 9th or so magnitude. It depends on where you are. And again, if you have a big telescope, you can probably do 14th magnitude. Um,
All right. Well,
yeah,
thank you so much for talking with us this evening.
no problem. Thank you. Thanks for inviting again. Um, so shall I log off, maybe?
Yep. We'll have our president, Diane Hall, come back up here to close things out.
All right. Bye, folks.
Thank you so much again.
All right, everybody. Thank you for joining us tonight. As I said, this is our last meeting in this venue until September 21st. Please reach out to Jeff or me if you want to do the Cranbrook event next Wednesday or on the 27th. And Jeff will be rattling the cage about astronomy at the beach signups. So Normally we go to the Red Coat Tavern to do our customary gastronomy after astronomy. Some of us are going to have to skip that tonight, so we wish you good time, a safe night, and clear skies.
We could ask, please look around your seat if you have snacks and make sure it's clean around.
I was gonna have him, but I would think we could talk, because that's the time he's looking for the pulsar.
Oh, wow.
He's trying to find how